introduction. So this will be a Blackboard talk with this kind of font. So it's still time to go down if you cannot see that. It's, of course, my turn to thank the organizer for this beautiful conference. It's a pleasure to be here. Rio is a very terrific hiking place, I must say. I say there should be more information about it on the website of IMPA. They should put some information because, Evelyn and I have very nice suggestions of terrific trails that could contribute to reduce the number of mathematicians. But in addition to hiking, I'm sometimes interested in in two-dimensional viscous flows, and in particular in understanding getting qualitative information on the behavior of the solutions. Okay, so today I will consider a very specific question, which is how energy can be distributed in two-dimensional flows in large domains, or more precisely, flows with large Reynolds numbers. Okay, so instead of discussing this abstractly, I will just write a concrete question, a problem, which is easy to formulate, but to my opinion, not so easy to solve. So let me start with the following problem. Okay, I consider the 2D Navier-Stokes equations. So this one is very familiar in this conference. dtu plus u dot grad u is equal to Laplacian of u minus gradient of p. Sometimes I will put the viscosity, but the viscosity will be 1 in my talk, so I can write it wherever I want. But, okay, I will not play with the viscosity parameter. Divergence of u is equal to 0. So the notation are standard. U is the velocity field, P is the pressure field, and I assume that my space variable x is in R2, so I consider the problem in the whole two-dimensional plane. Okay? And what is a little bit maybe unusual, I will assume that initially, so I have to specify initial data for that system, and I assume that initially, the initial data, U0, are just bounded. I do not assume any decay at infinity. Okay? So in the framework of Navier-Stokes, it's not so common. In other nonlinear parabolic equations, this is very common. You want to consider solutions which are, for instance, periodic in space or have definite limits at infinity or things like that. And those do not belong to some LP space with finite p. So consider L infinity. By the way, in the framework of the NLS equation, we have seen that it's also useful to consider solutions which converge to unit circle at infinity, and this gave rise to the Gross-Pitayevsky equation. So here I consider that. And the questions are for this problem, so first question, do we have global well-posedness? In fact, the answer is positive. This is known, and I will recall what is known about this. Now, once this is settled, okay, so you have a global solution which stays bounded for all time. So now, if I compute the L infinity norm of the velocity field at any time, this is certainly a finite quantity, but may I take the supremum over all times, and is this bounded? Does the solution remain uniformly bounded for all times? Okay, so this question, as far as I know, is open, and in the first part of my talk, I will give sort of the state of the art about concerning this question. And the third question, if assuming that you have a positive answer to question 2, which is still not known, is how does u of t behave as t goes to plus infinity? Okay. So, of course, this question is not known either because we failed to give a complete answer to the previous question. So in the second part of my talk, I will solve completely this question, but in a particular case, not for the full problem. I will assume periodicity in one space dimension, and this simplifies considerably the discussion. Okay. Now, but before discussing this, so this is the plan of my talk, by the way. Okay, now, before coming into the first part, I would like to motivate briefly this problem, because maybe it's not so common to consider this setting. So you can imagine many motivations, but the one I have in mind is the following one. So let's do some motivation. And for the motivation, I go back to a finite, a bounded domain, but I assume that this is a very large domain. So I want to solve Navier-Stokes, 2D Navier-Stokes in a very large domain with, say, a no-slip boundary condition. So, of course, it's legitimate for you to ask what means large domain because you have scale invariance. So I mean that the Reynolds number is large. So we could define, for instance, in that problem, sort of a Reynolds number by saying L times U0 in L infinity divided by nu and ask this to be much larger than 1. And L is some typical dimension related to the domain, so why not to take here the diameter of omega? Okay, so this is what I mean by large. Okay, now, okay, so if I assume the initial velocity to be N infinity, this means that I have finite initial energy. Okay, so at initial time, I can compute E0, which is 1/2 integral over my domain of U0 squared dx, and this is definitely a finite quantity because U0 is supposed to be bounded, and the domain is also bounded. So I have a finite amount of energy, so I'm in the framework of finite energy solution, and it's well known now since 50 or 60 years that in this setting I have global existence of a unique classical solution to 2D or strong solution to 2D Navier-Stokes equation. Okay. We also know, so we have global existence in uniqueness for any domain, any smooth domain at least, but independently of the size. And we also know that the solution converges exponentially to 0 as t goes to plus infinity because I consider the equation without any additional force. So it's a dissipative system. I don't put any force. The energy gets dissipated. It will eventually converge to 0, and it's even known at which exponential rate it has to converge. This is, for instance, in the work by Foyage and so that was been quoted in previous talks. Okay. Now, this may give the impression that we know everything about the system. We know global existence, uniqueness, and we know what the solution does asymptotically. But, of course, this is not completely fair because all the interesting dynamics about turbulence and whatever has been discussed in previous talks, like inverse energy cascade or vortex dynamics or vortex mergers, this all happened during the intermediate times. So the long-time asymptotics are completely boring. You just go to 0. There is an asymptotic laminar regime where nothing interesting happens, but all the interesting dynamics is during the transients, okay? And this is, of course, much more difficult to describe. So we'll make no attempt to describe this precisely, but I will at least ask a very basic question, which seems natural to me, but for which I cannot find the answer so easily. So the question is as follows. You take now a subdomain, which is supposed to be small, a small observation ball, and you ask the following question. How much energy can I observe within that ball at time t? In other words, I would like to bound the quantity 1/2 integral over the ball b of u of xt squared dx for some given t. Okay? Do we have an upper bound on that? Of course, we have an upper bound, which is very easy. You can say always that this is less than 1/2 integral over the whole domain of u of xt squared dx, and this is less than E0, which is finite. Very easy bound. It holds for all times with explicit constant and so on, but that's more or less the only thing we can say in its favor because we expect this inequality to be horribly pessimistic. Okay. Suppose, for instance, that omega is the Atlantic Ocean, for instance, and B is a ball of radius 1 kilometer, which is located around your ship. Do you imagine that the whole energy of the Atlantic Ocean could suddenly be concentrated around your ship? This could produce a very interesting wave. So certainly you don't expect that. So this inequality here is probably nonsense. Okay, if B is very small compared to omega, this is true, but this is not what you want. Okay, so my point would be, is it possible to bound the energy in B in such a way that this doesn't depend on the size of omega? This depends, for instance, only on the initial energy density, but not on the total initial energy, which might be very large and is not located near my observation domain B. Okay? So I don't know the answer to that question, but I have the impression that if you want to make such estimate in a way that is independent of the domain omega, one natural step to go to this problem is to get rid of the domain, to work in the whole plane. So there I will be forced to do estimates which do not depend on the size of the domain because I have no domain anymore. So hence the question of studying this problem here with initial data which is just bounded. Okay? I assume bounded initial energy, and I would like to know whether I can control the solution. Okay? So this is my motivation, but okay. If you don't like it, you can find another one. Okay. Yes, I mean, yeah, this is the idea. Okay, so now let me discuss a little bit what we know about the Cauchy problem in that setting. So the first thing I have to know, I have to say is that before giving a meaning to that, we should indicate how we choose the pressure. So the first step is a preliminary step, is the choice of pressure. So the pressure is known to satisfy an elliptic equation, which has been written several times already in this conference. Minus Laplacian of P is divergence of U dot grad U in R2. Okay? But this doesn't determine the pressure uniquely because you can add an arbitrary harmonic function to the pressure, and this gives another solution. In a bounded domain, you don't have this problem. I mean, in a bounded domain with no slip boundary condition, this elliptic equation plus the equation itself determines the pressure up to a constant. But this is not the case here. So what do we choose? Well, I mean, since we want to solve this with bounded solution, and since we have a gradient of P appearing in the equation, it's sort of natural to choose a pressure so that gradient of P is bounded. If gradient of P is unbounded, there is little chance you can stay in the space L infinity. So this means that if you can find a bounded solution to that equation, what you can add to it is either a constant, which is completely irrelevant, or add some linear function of x. Okay. And a linear function of x, alpha times x1 plus beta times x2, will give you a pressure gradient at infinity. And if you put a pressure gradient at infinity, then you just get another dynamics that if you have no pressure gradient. I mean, this is very natural in fluid mechanics. For instance, if you consider the Poiseuille flow in a cylindrical pipe, you have a non-trivial stationary solution which continuously dissipates the energy, although you have no forcing term, no explicit forcing term in your equation. But of course, you have a pressure gradient at infinity which drives the motion. If you don't put this pressure gradient, you don't get the Poiseuille flow, you just get zero. Okay? So you just have different dynamics. I mean, different choices of the pressure give different possible dynamics, which are all very nice. You just have to choose the one which interests you. And in my case, since I went to the unbounded domain just to have estimate that are uniform in omega, it's natural to ask for no pressure gradient at infinity. So in other words, I consider the equation without any forcing term here and without adding some hidden forcing in my definition of the pressure. It's really the freely decaying turbulence without exterior forcing. Okay? So then the canonical choice is the following one. So P is the sum from ij running from 1 to 2 of Ri, Rj acting on Ui, Uj, where Ri is the Ries transform. So it's minus Laplacian to the minus 1/2 derivative with respect to I. Okay? This is the Ries transform. Okay, so it's given in Fourier space by a multiplier which is homogeneous of degree 0, and therefore in the physical space, it's a singular integral operator to which you can apply Calderon and Zygmunt's theory. So in particular, what you can show that the pressure P, if U is in L infinity, so the pressure P is not necessarily in L infinity, but it's bounded in the space BMO by a constant times U in L infinity square. So this is the best you can do in general. So I don't know if we can choose the pressure to be bounded. It could grow logarithmically maybe at infinity, but not worse than that. Yes?
Do you expect that if you choose a different P, it will affect the fact that the solution remains bounded in L infinity?
Oh, yes, it can. At least a priori, I don't know. I mean, so for the moment, yes, it can definitely. You are sort of adding a constant forcing to the fluid, and this can definitely change things. Okay, so this is the best you can do. So this is my choice of the pressure. So now the question is the Navier-Stokes equation with that choice of the pressure well posed in L infinity? Okay, so this is not a very difficult problem, at least as long as just local well-posedness is concerned. So for local well-posedness, so this was first done, I guess, or first published at least by Giga, Matsui, and Sawada in a paper in 2001. Okay? So this is not a very difficult argument because L infinity is very smooth. I mean, for two-dimensional Navier-Stokes equation, in terms of local regularity of function, the best you can, the worst you can accept is L2 initial data. I mean, initial data can have local singularities like an L2 function. Here I'm in L infinity, so I'm comfortably in the subcritical range for Navier-Stokes, which means that if I write, I take this equation, I eliminate the pressure by the Lorentz projection, I write the corresponding integral equation, and I make a fixed point in L infinity, this will just work, okay? And this gives local well-posedness with just a little caveat that I don't want to discuss, is that the Lorentz projection is not continuous in my space L infinity because it involves precisely, again, Riesz transform. But this can be avoided, and you have a local well-posedness. Okay. Now, can we extend the solution to global solution? For this, we need a priori estimates. Okay? So, next step is a priori estimates. So here, situation is a little bit complicated because, the only one that are easily available are the estimates which involve the vorticity again. So this is my only connection with vortices in the school. I will not discuss so many vortices, but at least a little bit from the vorticity equation. So you consider omega, which is d1u2 minus d2u1, a very familiar quantity, and it satisfies, of course, dt omega plus u dot gradient omega is equal to nu Laplacian of omega. Okay? So this very nice advection diffusion equation. Now I can assume without loss of generality that initially omega is also bounded, because if it is not, it will soon be due to parabolic regularization. So assume that omega is initially bounded. So what you have is that omega of t then in L infinity is bounded by omega 0 in L infinity for all positive time due to the maximum principle. So this gives you a lot of information on omega. But now comes an interesting question. What do we know about u from this information on omega? In bounded domain, you just take your formula for the Biot-Savart law, for instance, and in bounded domain, you don't have this information so easily. But in other situations, it might be that controlling omega allows you to control u. But here the situation is a little bit more complicated. Let's try to write a Biot-Savart formula. This is maybe possible. So let's try the Biot-Savart formula. So here I'm facing some little difficulties due to the fact that I have absolutely no decay at infinity for the vorticity. So what I claim is that so you can make a little lemma as an exercise, if u and omega are in L infinity of R2, of course, u should be divergence-free and omega should be the curl of u. Then what you have is that for all x in R2, you have the following representation formula. So u of x is equal to u of 0 plus 1 over 2 pi limit as r goes to infinity, integral over the ball of radius r over my variable y. And this is x minus y perp over modulus of x minus y square plus y perp over y square omega of y dy. This is a Biot-Savart formula that holds for, in this situation, when u and omega are both in L infinity, then they are related by this formula. This formula tells you that, of course, something that you can deduce easily by other ways, that if you know omega, then you can reconstruct the velocity field u up to a constant, I mean, two constants if you want, which is here the value at 0. By the way, 0 does not play any special role. You can translate all that, but this is typically what you can have. But the problem is that this integral does not converge absolutely, and if you only know that omega is in L infinity, you are not able even to show that this limit exists. To show that this limit exists, you have to integrate by part using the fact that omega is the curl of u and using the fact that u is in infinity. So you are running to a circle. You get information of u out of information from u. So there is nothing you can really deduce from that formula. And after playing for some afternoon with that formula, I deduced that it was just useless and that the best information you can have for u is just recalling that u is the orthogonal gradient of Laplacian minus 1 of omega. And then if you take first order derivative of u, these are expressed in terms of omega by applying Riesz transform again. So from that, you deduce that the gradient of u in BMO, again, is less than a constant times u, times omega in L infinity. So this is true, and I don't think that this formula contains much more information than what you have from this sort of simple or at least classical estimate. So you know that the gradient of u is under control, not exactly in L infinity, but close to L infinity, locally in any LP and things like that, but not more. Okay? So in principle, in particular, this doesn't tell you if the velocity field will grow unboundedly or not. It just tells you that if at some point u of xt grows, then in a neighborhood it should also grow, but doesn't tell you if it's possible or not. Okay, okay, now using this information of vorticity is quite easy to complete the global existence proof, because you can do it in the following way. I mean, all is based on this very classical identity. So for the global well-posedness, you can make the following remark, is that you use the identity that u dot gradient of u, which is part of the nonlinearity in the Navier-Stokes equation. This is 1/2 gradient of modulus of u square plus u orthogonal applied to omega. This is again true for any two-dimensional divergence-free velocity field if omega is the curl of u. Okay? So if you replace this into the Navier-Stokes equation, this you obtain the equation in the following form: dtu plus u orthogonal omega is equal to nu Laplacian of u minus gradient of p plus 1/2 u square. Okay? And of course, divergence of u is equal to 0. So you see that if you write this in this way, the pressure is modified. It becomes p plus 1/2 u squared. This is what you do when you derive Bernoulli's law for Euler. This is the quantity which appears in Bernoulli's principle. And then you have this nonlinearity. So suppose you can eliminate the pressure by applying the Lorentz projection. There is a little problem in L infinity, but let's forget about it. You obtain an equation in which the nonlinearity is now u orthogonal times omega. Okay? And now it's, instead of being quadratic, it's now linear in u if you consider omega as being under control. And omega is under control because of the maximum principle. So the nonlinearity, which was quadratic and therefore could lead to some finite time blow-up, becomes linear, and therefore the worst you can expect is exponential growth as t goes to infinity. Of course, there is a problem with the Lorentz projection here, and for that reason, you have to modify a little bit the argument. And what was done by Giga, Matsui, and Savoeda in 2001, they obtained out, using this remark and some tricks, that u of t in L infinity is less than a constant times exponential of constant exponential to constant times t for all t the constant here depends on the initial data in a way I don't want to specify. So double exponential growth, which certainly prevents blow-up in finite time, but looks a little bit pessimistic. I mean, probably difficult to construct a solution for which this is sharp. In fact, it's impossible because it can be improved. And this was done a few years after by Sawada and Taniuchi. So there is another paper, Sawada and Taniuchi. And this is 2007. And what they prove is the improved bound that U of t in L infinity is less than a universal constant, or this constant is universal, so times U0 in L infinity times exponential of constant omega 0 in L infinity times t. And this is, again, for all positive t. So it's still exponential, but now it's a single exponential, and you see the way where how U0 and omega 0 enter this formula is exactly what you would guess from this way of writing the equation. So this is sort of the natural bound you can obtain by the methods I presented so far. Okay? I think, but I am not sure, that this is the best you can obtain if you just use the conservation, the a priori estimate on the vorticity. Okay, but this is far from being sharp. Again, don't try to construct a solution for which you have that. You will fail because so far we didn't use a little detail, is that there is another quantity that is important in Navier-Stokes, which is the energy. We didn't use anything about the energy. We just use maximum principle applied to vorticity equation. Of course, using the energy, so this is energy or maybe local energy dissipation. Using the energy is a little bit more complicated now because, of course, I cannot compute the kinetic energy over the whole domain because, in general, it's infinite for the solutions I'm considering. So I have to do something else, and since I don't know what to do, I write the dissipation law in differential form. Okay? So this is time derivative of u squared over 2 plus divergence of u times p plus 1/2 u squared is equal to some flux term which is viscous, so nu Laplacian of u squared over 2 minus nu times gradient of u squared. So any solution satisfies for all x and for all t this identity here. Okay? So of course, when you are in a bounded domain with, I may say, no slip boundary condition, what you do, you integrate both sides over the whole domain. So the flux term here, the inviscid flux, if you wish, and the viscous flux both disappear due to boundary condition, and you are left with what is called the energy, the energy equality in that case, or energy inequality, which tells you that the kinetic energy is non-increasing with time, and you have this nice Lyapunov function. Okay. Here, of course, I cannot integrate over the whole domain, but I can try to integrate over a subdomain. If I integrate over a subdomain, then everything is okay. A bounded subdomain, but I will have some flux terms, and these flux terms have to be controlled, and this makes the problem non-trivial and therefore interesting. So all that has been done recently in a very nice preprint by, no, it's nearly published now, a very nice paper by Sergei Zelik. Okay? So the next, there is a Y again. Sergei Zelik from University of Surrey in UK. So he did what should have been done since a long time, namely sort of uniformly, localized energy estimates for 2D Navier-Stokes equation. It's not so easy because any way you look at the problem, you have to look to deal with the pressure term. Okay? The pressure term, if you integrate this over a subdomain, then you have the flux over the boundary, and this flux involves the pressure, and you have to control the pressure. or if you want to multiply the equation not by u, but by mu times a cutoff function, then by making the integration by parts, you will have derivative of the cutoff occurring, and the pressure term will not drop out, because if you multiply a divergence-free vector field by a cutoff function, in most cases, you then end up with something which is divergence-free. So you have to deal with this problem, and that was the non-trivial part. And I will write what is the theorem. It's not, in fact, this theorem is not in the papers by Zelig. It's just my reading of the papers by Zelig. So let me write this like Zelig plus epsilon. My epsilon is positive. And I will, so it's, okay, I will not rewrite a whole statement. I consider a solution of 2D Navier-Stokes with a bounded initial velocity and vorticity and so on. And the statement is as follows. Given a positive time, choose some r of t positive such that, so r of t should be sufficiently large. So r of t should be larger than a universal constant times square root of nu t. This is due to diffusion. Then r of t should be also larger than a universal constant times the L infinity norm of u0 times t. Observe that this is a distance, like r should be. And also, r of t should be larger than a universal constant times u0 in L infinity times omega 0 in L infinity times t square. This goes worse and worse, because this is square root of nu t, now it's t square. Hopefully we stop here. So you take r of t such, then what is known is that if I take the integral of our ball centered at, this is the ball centered at x with radius r of t, and I compute here the kinetic energy. So u of yt square dy. Okay? And then I take the supremum over all possible location of the center of the ball. Okay? So I compute the kinetic energy on a very large ball centered anywhere in the fluid. So this is less than a universal constant times the same quantity at initial time. So sup over x in R2 of integral over ball of x radius r of t, of course, u0 of y square dy. Okay. And this in turns, of course, but I can just finish here. This, if you assume that the initial data are L infinity, this is bounded by a constant times r of t to the power 2 times u0 in L infinity square. But I mean, the last estimate is trivial. So this is the result by Zelig when you push his arguments to their natural limit. Okay? So this doesn't look so terrific, but let me just mention a corollary that is maybe not immediately obvious, but I will explain, or try to explain a little bit about that. So you have a corollary here. Is that the lim sup as t goes to infinity of what? Of the L infinity norm of u of t divided by t is bounded by a constant times u0 in L infinity times omega 0 in L infinity. So now we see that u of t grows at most like t, linear in t, and this follows from Zelig's result. So this is really a drastic improvement. So you see, when you use some physically meaningful quantities, sometimes this leads to some improvement in the bounds. I mean, here you had a double exponential. This went to a simple exponential. Now it's linear in t. Each time we take a logarithm. So next step will be to show that it cannot go faster than log t, but for the moment, I don't know how to do that. Okay? So this is the best estimate I know so far. So since I anticipate that I will have no time to go to the details of the proof, let me just comment a little bit on this inequality and how this inequality implies this corollary. Okay? So first comment concerns, well, what do I do here? Why do I take this r of t sufficiently large? So let me make a completely stupid remark first, and then maybe this helps understanding the statement, is that, of course, although you don't know I mean, you cannot integrate the energy density over the whole space because it's not finite. You can try to average, okay? So if you take, for instance, lim sup as r goes to infinity of 1 over, r square, integral over the ball of x and radius r of u of x, no, not x, say yt square dy. I mean, given any solution, I can try to compute that quantity. So I average the kinetic energy over the whole domain, but of course, dividing by the measure. Or we can take pi r square if you want to have an average like that. So this is well defined, and this is a non-increasing function of time. Okay? Not very useful in most cases. I know it will be constant, but I mean, it's not a very strict Lyapunov function, but at least you have this under control. So this kind of flux terms that I mentioned when you do integration over a disk or a ball here, you can beat them by taking average over sufficiently large r. And this is just because when you increase the radius of a ball, the area is something like r square, but the circle, which is the boundary, grows only like r, okay? So when you divide by r square, you have some hope that at some point you can beat the flux terms by the bulk terms in something like that. And this is just a sort of a remark. So this is disconnected. This is not at all the argument of Zelig, but what I mentioned here is that you can quantify this a little bit more carefully, and you don't need to take the lim sups. If r of t grows sufficiently fast with respect to t, then this is also true. So that this is essentially a non-increasing function of time. Yes? I don't get anything better. No. You get the same if you were careful with your constant, and you deteriorated one if you are not careful, but this is just self-reproducing. But okay, we can discuss, but no, I tried, of course, but this doesn't seem to be so. Yes, Elena? Which constant? Oh, let me go to this one. This one also. Okay, let me make a comment. I wanted to make it later, but since this is for you, I will make it now. The whole argument of Zelig does not depend on the viscosity. Nowhere the dissipation of energy is used. So it's also valid for Euler. If you give me a solution, I don't know if in Euler, if you give me just U0 in L infinity and omega 0 in infinity, I let you tell me if you have a global smooth solution. I don't know. But if you give me one, it will satisfy this. I did. Yes, so this is definitely a space left for improvement. Zelig's argument does not use, it used the fact that energy is not created, but it never used the negative terms that are created by them. This is pretty remarkable, and that may think that this linear power AT, maybe it's optimal for Euler. This has to be proved. Then you have to construct examples. I don't know how to go further. But for Navier-Stokes, definitely one should be able to do something better, because if you don't use dissipation, of course, you cannot hope to get a sharp result. Okay. So this is more or less the explanation. I will not give more details because I have to enter a whole machinery, which is pretty standard, by the way, in people doing attractors on unbounded domains, but not so well known to people doing fluid mechanics in bounded domain. Okay. Now, the other point is, why is this estimate, what is the relation with this corollary? Well, I mean, for that, you have to use, in addition, the bound on the gradient of u, because it means that if you have, at some point, in your space, so I draw the space as a line. Suppose that the velocity, the intensity of the velocity field, so the speed of a fluid particle is large at some point here, close to its maximal value. Then, of course, it cannot drop down to something near zero immediately because you have a bound on the gradient of u. And forgetting for a minute the difference between BMO and L infinity, just to know that you have a Lipschitz bound on u. So it means that, okay, if you are big, you should stay big over a region, and the diameter of this region, of course, is a constant times m. So now you take the square of that, you integrate over the domain. This means that if at a given point, at a given time, you have a point where the velocity field has size m, then the energy computed over a sufficiently large ball should be at least m to the power 4. And this is bounded by this. But r of t, I can choose it as t squared, so this is t to the power 4. M is bounded by, m to the power 4 is bounded by a constant time t to the power 4, so m can grow at most linearly like t. Okay. So this is the proof of the corollary from exactly this. And if you take the explicit expression of r, you get exactly that. So this is very easy. Observation. Good. So this is all I wanted to say concerning the problem in R2. So there is an obvious open problem. Can we produce a solution, say, for Euler to the Euler, which is L infinity for each time, but for which the L infinity norm is not bounded? I have no example. And, okay, this is something that you... and if it's not possible, can you improve this estimate? Okay. Now I will go to the second part of my talk, which will be, I hope, a little bit shorter. I will cheat a lot because I'm stuck at this point, despite some recent progress. I would like to consider the case where everything is periodic in one space direction. So the periodic case. So instead of being in the whole plane, I am now in an infinite strip for which I apply periodic boundary conditions. So if you prefer, I am on a cylinder, a flat cylinder. So this is x1, x2. So the diameter of my strip will be L. I put some length here, and I consider this domain here, omega. My domain omega here will be R times the torus, the one-dimensional flat torus with L. Okay, like that. And I will refer to x1 as being the horizontal variable and x2 the vertical variable, although I don't put any gravity in my problem. It's just because this is on the blackboard. Okay. So now, so I assume now everything to be periodic, including the pressure. So that's important because in a periodic domain, you could have gradient of pressure to be periodic, but not the pressure. And this will be more or less equivalent to having some kind of gravitational field around the cylinder. But I don't, for the same reason as before, I don't put any hidden forcing in my system. So U and P are L periodic. U and P are L periodic in the vertical variable x2. Okay, I consider that. And, and I assume, as before, that my initial data are L infinity for U and for omega, because this makes statements easier. Okay? So I don't have to discuss the existence problem, because it's a subcase of the case of the whole plane, which I discussed already. So let me introduce quantities related to initial data, and I want to introduce some Reynolds number here. Reynolds numbers computed at initial data. So you can define a Reynolds number now very naturally associated to the velocity, which is L times U0 in L infinity divided by nu. L is now my L. U0 in infinity is the maximal initial speed, and nu is the kinematic viscosity. And for some reason, I also define the corresponding quantity for the vorticity, which is now L squared times omega 0 in L infinity divided by nu. Okay? So this could be the velocity and the vorticity Reynolds numbers, respectively. Okay. Now, I have a second theorem here about that case. So this is a collaboration, I should mention, with Sinisa Slijepcevic from the University of Zagreb in Croatia. Okay? And the second theorem concerns, of course, the periodic case. So I don't state the hypothesis again. I consider the 2D Navier-Stokes equation in this periodic, in this two-dimensional cylinder, and I assume that initially Ru and R omega are finite quantities. So I have three conclusions. In this setting, I can prove that I have uniform boundedness. For the velocity field. And I can even make a quantitative set statement, which is as follows. Suppose that I take u of t, I mean the L infinity norm of u at some time t, and to make it something like dimensionless, I multiply by L over nu. This is bounded by a universal constant times Ru plus R omega plus 1 plus R omega times Ru square plus R omega square, and this is for all positive time. So in that case, I know that the velocity field remains uniformly bounded for all times, and you should certainly not trust too much its expression, but I can quantify how big the Reynolds number can be in terms of the initial Reynolds number. Okay? This is the Reynolds number computed at time t, if you want. It's bounded by the initial Reynolds number to the power 3. This is the worst that can happen. I mean, velocity can increase. I don't have any maximum principle for the velocity, but not more than what is specified here. Okay? Second claim is that I have uniform decay of vorticity. The vorticity converges uniformly to 0 as t goes to infinity. So again, I take the vorticity Reynolds number, which is omega of t in L infinity multiplied by L square over nu. I take the square of it to make it nicer, and this is less than a universal constant times 1 plus R omega times Ru square plus R omega square times L over square root of nu t, and this is for all strictly positive time. So you see that the L2 norm, the L infinity norm of omega decays uniformly to 0 as t goes to infinity, at least like 1 over t to the power 1/4. Again, I don't know if this is optimal, but everything is explicit, so I can not only show that it converges to 0, but I can estimate the time it needs all the way from the initial data to reach some smallness. Okay? This is uniform decay of vorticity. And then the last claim is that, so this solves the question 2 in my initial problem, but on that particular case, I have global existence, uniform boundedness. And now what is a long-time behavior? So here you have uniform convergence to shear flows. So let me explain that. The last conclusion is that if you take u of t, and if you subtract some mysterious u infinity of t, which I shall define soon, I compute this in L infinity norm. I multiply by L over nu because I insist of having something which is dimensionless. This is order of exponential minus gamma nu t over L square as t goes to plus infinity, and here gamma is any positive number less than 2 pi square. It's really 2 pi square and not 4 pi square. I should insist on that. Okay, so where, of course, where u infinity of t is what? So u infinity of t, this is a vector field, so it depends also on x. I don't write the dependence on x inside the norm, but when I want to define the vector field, I have to specify it. So it has 2 components. The first one is a constant, and the second one is a function which depends only on x1 and t, okay? And, okay, so c is an r, constant. And what is m1? So m1 is an approximate solution of the heat equation. So dt m1 is equal to d1 square m1. This is a one-dimensional heat equation because it depends only on one variables, plus order of e to d minus 2 gamma nu t over L square. Okay. So it's, I should perhaps mention concerning this last part of the result is that if I take any constant c here And if I take here any exact solution of the, oh, maybe there is a nu here, of course, because of the, I put it in the equation. I take any solution of the heat equation without any correction here. This is an exact solution of the original Navier-Stokes equation. This is a shear flow where the horizontal velocity is a constant and the vertical velocity depends only on the horizontal variable. Therefore, it's a shear flow and satisfies just the heat equation. So this is the set of functions which are of this form can be thought of as a manifold of slowly varying, not equilibria. I mean, maybe Jean will call this metastable something, but okay, this is the idea. And you have a slow manifold on which, made of shear flows, which evolves according to the trivial dynamics of the one-dimensional heat equation, and all solutions converge exponentially rapidly toward members of this family. So this shear flow describes the long-time behavior of all solutions of my Navier-Stokes equation in this infinite strip. Okay? So this is, okay, I don't want to erase that. So I will probably just now make some comments about this statement. So this is much simplified compared to the original problem. It is fortunate that I don't have time to go to the proof because the estimate you may have for this result will reduce immediately when you see how simple it is in the periodic case. But okay, I will be saved by the gong. Okay, so let me think. What is the picture you see out of it? So when you start in this domain, it's still an unbounded domain. I mean, L is fixed, but okay, I have infinite space in the, it's like a one-dimensional unbounded domain, one unbounded direction. So you start with very, very turbulent initial data. What do you guess from this theorem? So you have first a long transient period in which 2D turbulence can develop. And in this period, you have inverse energy cascade, maybe you have vortices certainly forming and so on. Okay. And then you have a final asymptotic state where the influence of the boundaries are really felt. I mean, not the boundaries because there are no, but the finite size of the cross-section of the cylinder. And this drives exponential convergence towards trivial asymptotic states, which are shear flows. So you have long transient, so turbulent behavior, possibly turbulent behavior, and asymptotic laminar region. Okay? But since my estimates are completely explicit, I can tell you what is the lifetime of the turbulent period. Because the lifetime, so let me, maybe I can erase this cylinder here and draw a few conclusions about this result, some comments. So the first thing we can say is we can estimate the lifetime of turbulence in this case, okay? And this lifetime, let me call it capital T, is of course not defined uniquely because you have to, it's from the initial data up to the point where the vorticity is sufficiently small, and how small is, of course, is your choice. So it will be something like square root of nu t over L should be less than a constant times the quantity appearing here. So it's something like 1 plus R omega times RU square plus R omega square. So roughly, it's a 6th power of the initial Reynolds number. I have no idea whether this is sharp. It's certainly pessimistic, but it's not exponentially large or things like that. It's a power of number. Okay, and then you have the asymptotic laminar regime, which is characterized by the fact that L square omega of t in L infinity divided by nu, which is this vorticity Reynolds number, is, say, less than 1 or less than 4 pi square or some constant related to the Poincaré inequality. So this is the moment after which I decide that the convection term in the problem do not play a very important role and everything is driven down to 0 or to the shear flow by just the Stokes part of the equation. Okay? So this you can measure explicitly. Now it's interesting here because if you look now at this U infinity here, so this is a constant, and this is a solution of the heat equation with, of course, bounded initial data. A solution of the one-dimensional heat equation with bounded initial data converges uniformly on compact set toward constant, like 1 over square root of t, okay? So this means that uniformly on compact sets, your solution u of xt will converge to a constant, okay? So this has consequences because, of course, you have equilibria in this equation. I didn't discuss possible equilibria, but you have some equilibria of the form C1, C2, where C1 and C2 are constants. Of course, these are equilibria. I can even remove, I can, by Galilean invariance, I can put everything to 0. So these are certainly the most trivial equilibria. These are the only equilibria in my equation. They are all because of this convergence result. If you have a non-trivial equilibrium, then, of course, it contradicts immediately that. So this is the only family of equilibria which are bounded and periodic in one dimension. There are no possible, and there are no non-trivial time periodic solution or recurrent solution in any sense of dynamical systems. Everything that is sort of recurrent should be just that. Okay. So this is not immediately obvious from the equation, but this can be deduced easily from this result. Also, there is something that is very peculiar, because this means also that in this model, you have uniform convergence on compact sets toward the family of equilibria. All trajectories do that, and this in the language of abstract parabolic equation, this is called sometimes quasi convergence. With respect to a topology, so my topology here is uniform convergence on compact sets, but you don't converge necessarily to a single equilibrium, but towards the family of equilibria. And this is typically much stronger than what you can prove in general for nonlinear parabolic equation on the real line. With that guy, Slijepčević, we developed sort of a theory of some abstract framework which is supposed to cover what we call extended dynamic dissipative systems, which is like PDEs on unbounded domain which have a gradient structure. And by considering several examples, I can just summarize what we know. We know that in such systems, the best you can hope for is uniform convergence of compact sets towards the family of equilibria, but not for all times. For all times, except for some exceptional excursions out of the set of equilibria. And this typically happens in nonlinear parabolic equation. Let me give you an example, which was considered in previous talks, but in higher dimension, in one dimension. If you consider the Allen-Kahn equation ut is equal to uxx plus u minus u cube. In that case, you can produce some initial configuration, make some kinks and anti-kinks and so on, for which the solution do not converge uniformly on compact set to the set of equilibria. This is proved. And another equation which is interesting is Burger's. If you take viscous Burger's equation, ut plus ux is equal to, say, uxx, x in R, you cannot prove that this equation converges to uniformly on compact set to the set of equilibria, even if you include in the set of equilibria all the shocks and their translate, is just not true. Okay? So, in fact, in the Burgers, I'm not even sure that for bounded initial data, you cannot construct a non-trivial trajectory that is periodic or quasi-periodic in time. This is not even clear. So my message here is that 2D Navier-Stokes in a strip, this is much, much simpler than 1D Burgers equation. 1D Burgers is supposed to be a simplified model of Navier-Stokes. You can consider it even really in 1D, whether I'm in 1 plus 1D and a half in some sense, but Navier-Stokes is much simpler. You can dynamically, you can provide much more complicated solution of that than of 2D Navier-Stokes. This is absolutely clear. Okay? Well, I don't know when I started, but I finished with the comments of my theorem, so I suppose I can stop here.
Questions? Idris?